So my presentation was on quantum computers' effects on the future of encryption. So what is encryption? Encryption exists to maintain confidentiality on data. It transforms the data so that anyone who's not authorized to see that data shouldn't be able to see it. Common misconception, because I will be using the terms, is hashing does the same thing. It does not. It's there to ensure integrity, so that if the data is changed, we can essentially make sure that, hey, it's been changed, something's wrong here. And that can happen in transmission if someone gets a hold of it and changes it. So mainly I'm talking about asymmetric key encryption. So this has two different keys. You have the public key and your private key, or secret key up on the graph. The public key is just like a lock. All it does is it locks the data and no one can open it except for the one person who has the private key. This makes it a lot more beneficial than symmetric key encryption, because you don't ever have to give anyone your private key for decryption. Some of the methods that we use today are RSA, Diffie-Hellman, elliptic curve. RSA is extremely popular, and we use it just about everywhere online right now. It's built around the factoring problem. You'll know that most encryption is built on some mathematical problem. And elliptic curve is also becoming more popular. It's based on the logarithm problem, which I'd love to talk about, but that's another talk. So just going on Bank of America's website, a lot of websites, you can see there's RSA encryption, and the key size is 2048 bits. Generally, when you have a bigger key size, there's more security, but you want to optimize, storage space versus, security as it gets bigger and bigger. How beneficial is that? Also, it has SHA or SHA-256 padding, which basically just adds bits to add security to it, so that if someone was able to factor the number, it would still be secure. So a little bit of number theory here. We know that we have prime and composite numbers. With prime numbers, the only factors are itself and 1. Now, when you multiply two prime numbers together, you get a number that's essentially semi-prime, which basically just means it obviously has other factors than itself and 1. And why I bring this up is that is essentially the whole problem behind RSA, is that the time complexity to factor an extremely large number, it exponentially rises as the number gets bigger. And so that's how our cryptography is built around. We have extremely long numbers, and for someone to factor it, it could take them years and years to do so, and so that they won't even try. So you'll see I have a little play. I have a little diagram. It shows that this axis right here is the size of bits, and then the red line is how long it takes to multiply two numbers together. Now you'll see that the blue line, which is how long it takes to factor, exponentially rises and it gets bigger and bigger and bigger. And this is very, very small numbers we're talking about, but as you can see, it'll eventually get to minutes, hours, and so on and so forth. And so you kind of get the idea here. And you can see that multiplying is pretty trivial at this point, as far as that goes. So quantum computing, the concept of quantum computing has been around since the 80s. The idea is that we can use properties of quantum mechanics to enhance our computing power. So the reason we want to do this is quantum computers are very good at certain problems. For example, optimization and exponential time complexity problems, like we just looked at, they're very good at them. Optimization being something like we have a wedding table with 10 seats, how can we arrange people? Or possibly like a maze, what is the best way using the least amount of turns to get through? So how is quantum computing different? There's a lot of information up here, but I'll try to sum it up as best as I can. Classical computers have bits, which are 0 and 1, as you may know. And then quantum computing, they have qubits. And they can be in a state of 0, 1, or some complex in-between state. The best way to think about it basically is with a coin, where you can have heads or tails. With quantum computers, when I flip the coin or spin the coin, it's in some position in between the two where you have a probability of getting heads or tails while it's spinning. The important thing to note, though, is that when we measure it, which is right there, it has to be in one of the two states. It can't be in some weird complex number state. And so this gives us a lot of power of quantum computing. The only point that I wanted to show here with this slide really is you can see this A and B here. This is actually how you represent qubits and their states. And the A and B represent probabilities. So you can have like a 75% chance you're going to get 0 and a 25% chance you're going to get 1. You actually see it's very easy to visualize one qubit straight up as 0, straight down as 1, and you can see this orange line is some complex in-between state that has a probability of getting 0. This one is probably going to go towards 0, but it could be either 1. Now, entanglement is kind of the main power behind quantum computing. It's a relationship between two qubits. We don't really have an analogy towards classical computing because it just doesn't happen, but it's just, you can't talk about, so if two qubits are entangled, I can't say what the state of one is without talking about the other one. They're specifically related. A little fun fact, Einstein called this spooky action at a distance, because they could be across the galaxy, but entangled. But how do quantum computers actually solve problems? Most people say that, oh, quantum computers can see every solution at once. This is not true. I found a little comic, actually, it was kind of interesting. It used it like a talk, like you were talking to kids about different life things. But basically what this is saying is that quantum computers actually use constructive interference and destructive interference to amplify the wavelengths of the probabilities that we want while decreasing the ones that we don't want. So that kind of means that if you run a quantum algorithm, there's a chance you won't even get the right answer the first run around. So why does this matter and how does this affect encryption? Well, Shor's algorithm, which was in 1995, kind of proved that our encryption is in trouble. As you can see, our best attempt, our best known way to factor in a classical computer, you can see as the number of digits gets longer, it still gets very hard. But with Shor's algorithm, it doesn't get much harder once you get past 25, 50 bits of data. So that was the whole point behind Shor and his algorithm that he discovered. And I'm going to talk a little bit about it. It's a lot of math that will show up really quick. But with Shor's algorithm, the whole point was that you have an input and output register like a normal computer, and we have a number of bits, and we're just trying to get we're trying to find the period of a factoring problem. And you'll see here that the period is a repeating pattern. So when we're talking about this period, it's 1, 7, 4, 13, 1, 7, 4, 13. And the idea here is that if we can actually, let's say we get 1 when we measure, because we're only going to get one of these answers, that we can, with the qubits being entangled, once we measure that, on the input, we have an equal probability that we're going to get each one of those inputs that gave us 1. So 0, 4, and so on. And so basically, without getting too much into some of the formulas that I have on the board, we use the quantum Fourier transform, which is basically the quantum analog to the discrete transform, which essentially just amplifies the chance we're going to get the correct answer, or that answer, and then we can measure, hey, the period is 4. And we get our factors. And it's actually been proven we can factor 15. We do have quantum computers that are very experimental. But what does this mean for the future of encryption? Well, there's a lot of different factors. One of the problems with quantum computer is that we don't actually have a perfect one yet, and nowhere close. And our biggest one is about 72 bits. I believe Google has one. So the idea here is that we need a lot of qubits, and there's a lot of error correction to be done. If there's really any errors, that's a problem and doesn't really work properly. So it takes a while, and we're improving our methods of creating quantum computers even now. Also, there's extra padding on RSA to try to increase it. If we can factor it, the padding probably won't help too much. So post-quantum cryptography, there's a lot of, we know that RSA, elliptic curve, Diffie-Hellman, and Bushman-Williams will probably become irrelevant because quantum computers will be able to factor them. Michaelis and lattice-based cryptography are actually older methods, but have proven to be immune somewhat to quantum computers. Error correction is behind Michaelis, which just means that I'm going to send a bunch of data, and if it has errors in it, that's fine. If zeros change to ones and ones change to 0, that's fine. But we're also transmitting a way to decrypt that, or the person with like the private key will have a way to decrypt that and get away those errors. This is just some of the math. It's essentially a series of matrices that are going across, and Alice essentially encrypts your data with that. So Michaelis, the problem with it is that the keys can be very big because you're essentially giving a whole bunch of data and being like, if it has errors, just fix it. So the problem here with implementation is we don't really know how easy it would be with such a large key size. It'd be way bigger than RSA. and it might even slow down, let's say, web browsers or whatnot. So there's not a lot of implementation done on that. Lattice-based, there's a bunch of different problems here. The main one is learning with errors. It's also very similar to Michaelis. It has a mathematical problem where you're saying, oh, it's hard to know what S is given T and G. And obviously there's a lot of math here that I don't really have time to talk about. So what does the future mean? Why aren't quantum algorithms being discovered more frequently? Peter Shor himself actually wrote a paper about this, and he said that one possible reason is that maybe quantum algorithms are so different from what classical ones are that we just don't know how to think about that yet. We do know how quantum mechanics work, but how do we translate that to an algorithm? Another reason is that quantum computers are really only good for a select few problems, like factoring. You know, maybe quantum computers, although everyone says it's going to be the downfall and it's going to take over our computers, maybe it's not that great. As far as the future goes, I personally think that we need to do better work on implementing like Michaelis and you know, in actual implementations, and in the meantime, actually using quantum computers to create a new kind of encryption. Quantum computers are very good at creating random numbers that are, you know, truly random, and there's a lot to be done there with probability fields and how you can essentially, you know, you only get a certain probability of getting the correct private key, and there's some research to be done there as far as new encryption standards go. So yeah.
I thought it was a really interesting presentation first. My question is the complexity of the key or the encryption tied to like improvement in that key? Like I think about like the idea of like a one-time pad, for example, like something like simple. Is like a more complex answer that is always like can be solved by quantum computing always going to be a stronger encryption?
So I'm sorry, I don't really quite understand the question. So you're saying if the key size is bigger,
right,
is that more secure?
Is it always going to be more secure? Yeah.
So kind of. I mean, you saw like 2048 bits. That's kind of a magic number. 4096 is also another magic number. The problem is that as you increase the key size, the data gets bigger, and that's more prone to errors. So with transmission, right? If I'm transferring a bunch of bits, there's a possibility that I'm, you know, going to get more incorrect bits. And so it's kind of a perfect balance of we don't want a key size that's too big because it have a lot of problems, but we still want to maximize the amount of securities. It's kind of like a sweet spot.
Other questions? I asked a few. So I was actually going to ask you about like the factoring algorithm, and then you mentioned that Shor's is the fastest algorithm out there.
Mm-hmm.
Do you know what the complexity is? Like it's exponential, I understand. But
yeah, I actually have a slide. It's, I believe, right here. D to 1/3 time. So it's a constant times d to the 3rd power. So the constant being the number you're trying to factor.
D is another digit. Okay.
Yeah. Yeah. Sorry.
I see. Thanks. And one thing I want to mention, you kind of had this good example of superposition of qubits, and then you jumped into entanglement. Kind of, it was unclear like how superposition is going to actually kind of be like it's connected to the entanglement,
right,
and how the whole concept is going to help you develop better like encryption keys.
Right. So there was a lot of encryption that I couldn't include, or at least with Shor's algorithm specifically. So the idea here is that, especially with Shor's, we're trying to get as many input qubits as possible to maximize the chance that we're going to get like the correct number. And so how that deals with superposition is, as these qubits are put into a state of superposition, once we measure those and they're entangled, right? Once you measure one, you know, that flips to 0 or 1, and then measuring that one, because it's entangled, changes the other ones. And so by doing that, we're eliminating whole possibilities all at once. We can analyze them much faster.
So the concept is this, like you have, like let's just, for simplicity say you have 2 qubits, right? Of course they're in the superposition until you measure them. But once you measure this one, because of using the entanglement theory, you can actually figure out what the superposition of the other.
Yeah, partially collapses the other.
Thanks.
Yeah.
This might be a gross and uneducated oversimplification. But if we have these super powerful future computers that can encrypt
Yeah, so well, quantum computers, the whole point is that Shor's algorithm actually does decrypt. It's the whole point of Shor's is that it's very good at dealing with exponential time problems
Okay.
like RSA, and it finds the solutions, the factors, much easier by kind of breaking down the problem into a period problem. Actually, what's not clear is that Shor's algorithm, only part of it is quantum. So a lot of it you can actually do on a normal computer. The only part is finding the period, because something I probably didn't make clear is that the period can be almost as big as the prime number. So given some prime number that's 100,000 digits long, the period of it, you know, that pattern that kept repeating could be just as long, and that's why it's so hard to find the factors. Is that even if you're trying to find the period on a classical computer, it's not very easy to. So yeah, so my point at the end was that I think that quantum computers, there's not a lot of research done into how they can be used to make new ways of encryption. We have these ways of, okay, we can break RSA because we can factor super easily, but there's no one really doing much on creating new methods of, okay, how do we make a new encryption that won't be broken by quantum? Because on classical computers, we made encryption standards that can't be broken by classical computers, so why can't we do the same for quantum?
All right, let's thank the speaker again. Thanks to all of you for attending this